Hi, I'm Tobin Porterfield. Welcome to Module 4 and Part B, where we're going to look at discrete probability models. Now, in a discrete probability model, what's specific is not that they're on the down low or the hush-hush, but they're discrete because the outcomes from those trials are specific values. Rolling a die, you can receive a 1, a 2, a 3, a 4, a 5, or a 6. Flipping a coin, you get a head or a tail. Going to work, you might stop at a traffic light or not have to stop at a traffic light. So they're going to be yes or no type situations. We're going to look at 3 specific models. Oh, not those models. We're actually going to start with the Bornelli model, who was Italian but not a model. He was a mathematician, and he gave us some information on very specific situations, and those are those binary outcomes where we'll consider them to be either successes or failures. So pass a class or fail a class, get through that traffic light or don't. And if we're trying to get a heads versus a tails, then we flip the coin. What's the probability that we get that heads? The other item that he helped us lay out is that there's a probability of the successful outcome, and there's also the probability of the unsuccessful outcome, and it's up to us to define which one is which. And we'll use the letter P to designate that successful outcome, and Q, which is, of course, 1 minus P, as the unsuccessful outcome. Now, some other texts and other sources will use other variables to identify that P and Q, but it's still the same basic concept. The other item that Bernoulli brings to our attention is that the individual trials must be independent. So if I flip a coin and get a head, and then I flip the same coin again and get a tail, was there any influence that would have said, hey, I've got a head the first time, so I will naturally get a tail the second time, or a head? So is there any influence between those trials? And in the case of a coin, there is normally independence where there is no drivers between those two. So let's try out Bernoulli and see how we can actually apply it to some of our own decision making and information. So I set up this situation. You're taking a 10-question multiple choice stats quiz, and you haven't had time to study, so you've decided, since it's statistics, you'll just randomly choose between each of the 4 answers for the 10 questions. Since they're A, B, C, and D, you'll just randomly, blindly choose one for each question and hope that you receive that 80% that you need in order to pass the quiz. So some of the things that we know then, that if each question has 4 answers and only one of those 4 answers in each question is correct, then that's a 1 in 4 or 25% probability of success, and that we need to see that across each of the 10 questions at least 8 out of 10 times in order to pass the quiz. So some things that Bernoulli showed us then is this equation, and we see in the parentheses that N and the K. N is the number of trials, so there's 10 questions in our quiz. K is the number of successes. Well, we're going to need to be successful in 8 out of 10 guesses if we're going to pass this, so K will be 8. Now, hold on to that N and K for just a minute, because we're going to treat those a little differently, and let's move to the right. P is the probability of success, 0.25. K is the number of successes we need, which will be 8. Then times the failures, which is 0.75, and N minus K, or 10 minus 8, which is 2. So we can substitute in those values, and I've done that here. But how are we going to treat that 10 and 8 that were in parentheses? They're not just a 10 and 8 floating out there. They're actually what we call factorials. And if you see in the bottom of the left-hand box, that's how we would write those out in an expanded form. And we see N exclamation point, and that means take whatever N is, which in this case is 10, and multiply it 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So all the way down. So wherever we are, we go all the way down to 1. We multiply all that out. On the denominator side, that K is K factorial, which in this case is 2. 2 factorial, 2 times 1. So we don't have to go too far on that. And then N minus K factorial, which is going to give us that same, oh, I'm sorry. Back up. On that factorial, that K is actually 8. That would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And then times N minus K, which is 10 minus 8, which is 2. Not too difficult factorial, 2 times 1. So we can put all that together, and we find out that our probability of passing this exam is 0.000386, or if we make it a percentage, still 0.038%. So not very likely that we're going to pass this test just by randomly selecting from the 4 multiple choice under each question. Sounds like we're better off to study a little bit. But that's something that Bernoulli helps us do, is to predict outcomes based on these binary results. A couple other things he shows us is that the mean of a binary type of experiment is n times p, and the n from our previous screen, the number of trials, p, the probability of a success. The standard deviation, the square root of n, the number of trials, p, the probability of success, and q, the probability of failure. So in our example where we have the multiple choice questions, we have the expected outcome, so that over time we expect that we would see students receiving a 2.5 out of 10 if they continued this blind guessing, this random guessing solution. And then the standard deviation of that would be 1.875, fairly small standard deviation, very low result, so it looks like students overall are not going to be passing that test unless they study. Second model I want to look at is the geometric model. The geometric model is actually an extension of the Bernoulli situation where we're dealing with those binary discrete outcomes. So this model is used when we want to know how many trials will need to occur before hitting our first success. So if we're flipping a coin, how many times will we need to flip this coin before we get a head if we consider heads to be a success? The geometric model is driven by primarily one parameter, and that is that p, that probability of success. So let me give you a sample. The p we're going to use in the equation is p, the probability of success, q, the probability of failure, which we've talked about before. The other key value we'll need to know is the number of trials, how many times. So derived from that are a couple equations. We have our expected value, we have our standard deviation. And let's put this to work once. The universal blood type is O negative, and it's found in 6% of donors that come through the door to our blood drive. So if we're having our blood drive and we really need O negative blood, let's say there's a special case up in the pediatrics ward, and so the donors start coming through the door, how many donors do we expect to have to process before we encounter that magical O negative donor? Well, we already know the long-term probability is actually 0.06, so what we really would like to do is then extend that out to figure out how is that going to affect the number of donors coming through the door. So we really can just use our expected value, that mu, which is 1 over that probability, so 1 divided by 0.06. And we find that 16.67 donors, or almost 17 donors on average, will have to come through the door before we hit that first O negative donor. Just a little application of the geometric model. The third one that I would like to cover is a little different, is the Poisson model, and it's the model of unlikelihood. It's the model that we often use to test an unlikely situation. So the model in general is used whenever predicting the number of events that will occur given an interval of time. So people per hour, customers per minute, phone calls per day, those types of things. Poisson is a good model to consider whenever the data consists of counts of occurrences. Here's some things about it that we'll need to know. First off, we're going to introduce a new Greek letter. That's the lambda. And we're going to use lambda as the measure of the mean number of occurrences. So over time, what is our experience? How many calls do we receive per hour over the last 20 years or 10 years or 5 years? So over time, what's our expected outcome? And then x is the number of outcomes we're actually interested in. Interested in testing, that would be. So we have a couple equations we can work with. And so we see the probability of that occurring, probability of seeing the outcome that we are, is this equation. We see the lambda come in to the x, so the x is the number of outcomes we're testing. E is something new for us as well. That is a mathematical value, and it is a constant like pi. If you remember what pi is, E is one of those, and E is always 2.71828. So if you see E, we'll just substitute in that value. And then in the denominator, we see that x factorial, and so whatever that x is that we're testing, let's say 10 again, it would be 10 factorial, 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Our expected value over time is lambda. So over time, we expect to see what we've seen. And then the standard deviation is the square root of lambda. So let's try one of these out. Students are sent to the principal's office randomly on Friday afternoons at a rate of 2 per hour. So over time, our experience is that we see 2 students each hour on a Friday afternoon sent to the principal's office. What's the probability of having 5 students arrive in 1 hour on a Friday afternoon? So we're going to use our equation that we just saw to calculate what that probability would be. And we would say that what's the probability of 5 given that we experience 2 normally, lambda of 2. So we take the 2, the lambda, and we do it to the exponent of 5, which is our x. We've substituted our e value, 2.71828, to the exponent of negative 2, negative lambda, and divide that by our factorial 5. So it'd be 5 times 4 times 3 times 2 times 1. And we find that that likelihood is 0.036. Now let's look at the application of that a moment. The situation would be that over time we expect, and we've experienced, 2 students each hour on a Friday afternoon. On this particular Friday afternoon, we're starting to see 5 students each hour sent to the principal's office. And what the Poisson allows us to answer is, given that over time we experience 2, what's the probability that you'd ever have 5? And when we plug that in, we find out that that likelihood is very low, or 3.6% likelihood. And that would suggest to us then that this isn't a random event that we're having 5. There's actually something driving this. There's something going on in the student body. There's something going on in the faculty. There's something going on in the environment that is motivating or driving that we have 5 students, because it's very unlikely that under random situations we'd see 5 students. We also use the same model when we're testing quality. If over time we see 2 quality defects per unit of output, and then suddenly we start seeing 5, we would test what's that likelihood that we'd see 5 when we normally see 2. The answer would be 3.6%, which would be very unlikely. That means that it's very likely that it's not random, there's something actually driving it. So Poisson actually is used to test the probability of a very unlikely thing occurring randomly. So those are 3 models. They're rather unique, but I wanted to expose you to those. If you're using the standard textbook, then I've selected these problems for you to try. If you're using the online MyStatLab, then I'll have an assignment out there for Module 4 Part B, so you could try a few of these and just test your skills and see if you've got these situations under control.